I want to tell you about some things that folks in our group are working on right now. And a lot of that's going to have to do with black holes. But I'm going to highlight a couple other exciting areas as well that all sort of center around this challenge of linking microphysical and macrophysical scales in astrophysics, which I think everybody here knows is one of the central challenges of astrophysics, both observationally and in theory, and in simulations like the kind of things that we work on. So I'm going to start with a couple of just brief highlights, trying to give a couple of examples of this challenge, mentioning work from some fantastic students who are defending their PhDs and applying to CCA, among other places at the moment. One example where this is very important is astrophysical dust, and especially want to highlight work by a graduating student, Nadine Solomon, as well as former student Eric Mosley, who was at Princeton and just started his postdoc. But the idea is, okay, if you do planets, you know that dust has all sorts of incredibly complex dynamics and is incredibly non-trivial dynamics. If you don't do planets, or planet formation more specifically, most astrophysicists think dust is just something that sticks onto gas and bothers you by, blocking light, or maybe occasionally lets you do interesting things with polarization. But dynamically, we tend to say, well, the dust, is just moving with the gas. It's glued to the gas. It might get formed or destroyed, but it still moves with the gas. And that's just wrong, basically. A dust grain is huge compared to the molecules or atoms or ions it's moving through. And so it moves like a very massive aerodynamic particle. In fact, from an aerodynamics point of view, some of the characteristic dimensionless aerodynamic parameters of a dust grain, for a 0.1 micron sized dust grain in the interstellar medium, it has the same dimensionless aerodynamic parameters as a 2-meter sized boulder moving through a protoplanetary disk, basically. And nobody would call a 2-meter sized boulder a speck that's just entrained with the gas, basically. So we shouldn't call 0.1 micron sized grains specks that are moving with the gas. And they actually can move very differently, especially if you have something like light shining on it, where the dust will absorb the light and get pushed through the gas. And in fact, a few years ago with John O'Squire, we showed that this situation of dust being accelerated through gas is generically unstable. In fact, it's always unstable to an infinite sort of superfamily of instabilities that we call the resonant drag instabilities. And here's an example of what that looks like. You start with a homogeneous box of dust grains. This is just one of that family of instabilities. You push the dust, and it very quickly starts forming these structures on a huge range of scales, including scales much larger than the sort of collisional mean free path between dust and gas. And it's also size dependent, because different size grains have different aerodynamic properties. So you start seeing, the small grains form not just independent, but qualitatively different kinds of structures from the large grains in this simulation. And Nadine's done a number of projects to look at how this affects different astrophysical environments. You can look at how this affects things like winds. She looked at this in AGN winds in the sort of Taurus region, where dust would get hit by radiation and potentially launch radiation pressure-driven winds. And it can lead to all sorts of really cool structures. These are more GMC-like conditions, where I'm highlighting some of the nonlinear dust structure that occurs in these winds owing to these instabilities. And some of these look a lot like some beautiful structures and filamentary things that we see in molecular clouds. There's a host of projects that she's worked on that involve this. Another one that isn't out yet, but I wanted to just mention very briefly, that she's finishing up and should be on the archive in maybe a week or so, is she came up with an interesting idea. I've had a number of conversations with Ramon in the back of the room about this already, about how you could use this process to generate magnetic fields in the early universe. So when you think about how does the universe create magnetic fields, you generically are trying to think of different battery mechanisms where you try to generate some charge separation that generates a current and an electric field. And there's well-studied, decades-old battery mechanisms, things like the Biermann battery and more modern variants where you have things like plasma instabilities like the Weibull instability amplify Biermann-like terms. But those generally are pretty weak unless you have extremely weakly collisional plasmas, basically. Those methods operate best when the plasma is barely collisional, which means very high temperatures and very low densities. So they work great if you're talking about the outskirts of a massive galaxy cluster, for example, 10 to the 9 Kelvin and 10 to the minus 6 particles per cc. But that condition is incredibly unlikely to occur in the early universe at redshift 15 or redshift 10, basically. Gas there is dense and mostly neutral and relatively cold from a plasma physics point of view. But the idea Nadine is currently writing up is that if you have anything that shoves on dust, like light pushing dust grains are basically always charged. They're very good at soaking up free electrons. So you generate a current, and these things like these resonant drag instabilities, even if the medium is homogeneous, immediately generate inhomogeneities that generate the current generates an electric field that generates a curl of your electric field that generates a rapidly growing B. And you can compare this in those kinds of ISM conditions to something like the Biermann battery, and you get that this mechanism is at least 10 to the 12 times stronger than the Biermann battery. So it's potentially very interesting for those environments where those other batteries might not be efficient. Lots of work needs to be done, but it's a really cool idea worth exploring. And I could give a whole colloquium about the papers Nadine wrote this year, basically. She's had a number of other interesting results about how this, how dust can affect the thermodynamics of star formation, and can explain some interesting abundance patterns. Uli here has also worked on things like the dust in outflows for things like variable stars. Nadine had an interesting paper a few months ago pointing out that you can explain certain unusual refractory element patterns in stars through differential accretion of dust as those stars form in a way that is usually when we see these patterns, we interpret it as the stars having eaten certain types of planets. The problem is we're starting to see way too many stars that appear to have eaten planets to be sensible, because there aren't that many super short period super Earths for them to eat, basically. So a lot of cool stuff that links these small and large scales. Another example linking small and large scales is cosmic rays. And this is something our group has worked a lot on, and I'm just going to mention a couple things briefly about. Again, I could give a whole colloquium about cosmic rays and a lot of interesting astrophysical puzzles. These are charged particles, and the ones that, if you care about their effects on the interstellar and intergalactic medium, are most interesting are GeV protons, which have gyro radii of order in AU, or maybe a little less than an AU. And they gyrate around magnetic field lines. And those microscales matter because on macro scales, you can in principle have cosmic ray pressure act on gas, or cosmic rays heat the gas. But on microscales, it's those, if you have fluctuations in the magnetic field on scales of order their gyro radii, the cosmic rays can be trapped or confined and bounce around, confined by those magnetic fluctuations. And that regulates how fast they can escape or not escape from a given region of the ISM or the galaxy. And that part on small scales is incredibly poorly understood from a first principles as well as from an observational point of view, because we don't have beautiful resolved observations of sub-AU scales in the diffuse ISM, let alone CGM. And as a result, you can kind of get any answer you want for, are cosmic rays important on larger, say, galactic scales? So here's two simulations, which are both perfectly allowed by present-day constraints on cosmic ray physics. In the top, cosmic rays effectively do nothing. And this is a simulation of a Milky Way mass galaxy. This is showing on the left sort of the virial radius, where the halo is mostly filled with hot, hydrostatically supported virialized gas. On the right, you're looking at flow lines out to a megaparsec, where it's basically inflow onto the halo, and that egg-shaped thing is the virial shock on the galaxy. Now, let me consider a different model that's equally allowed by observations, where cosmic rays are efficiently, in this model, cosmic rays are not confined in the circumgalactic medium. So they get out of galaxies and they effectively stream out very efficiently without doing any work on the gas in the CGM. Here's a model where cosmic rays are efficiently confined in the CGM. and they're trapped, and you bottle up a large cosmic ray pressure in the CGM, it becomes dominant, and it can support a lot of cool gas that would otherwise precipitate out onto the galaxy. And they re-accelerate galactic fountains and trapped outflows into large-scale outflows that break out. And those ideas, to be clear, have been around for decades. We're just able to simulate them now for the first time more self-consistently, and I think people are just really starting to appreciate in the galaxy community how big an effect this can be and how much it really depends on these microphysics here. So there's a number of papers by folks like Irina Butsky and others that have looked at this possible range of effects. And we've tried to calibrate this. There's things you can do to try and calibrate those transport coefficients by comparing to different observations. There's a student, Isabel Sands, who's been doing work making synthetic gamma ray maps and spectra of the galaxy to compare to different models. And this is very interesting if you care about things like the galactic center excess in gamma rays. She's got some detailed models of that showing that at least some aspects of that may just be us overinterpreting galactic weather rather than an unusual population of either millisecond pulsars or annihilating dark matter. Maybe, but nonetheless, you can reproduce a lot of those signatures. Another student, Margot Fitzaxon at UT Austin, has looked at the cosmic ray ionization rates in molecular clouds, showing that there's some very interesting behaviors that make it difficult for cosmic rays to explain some of the indirect ionization rate signatures we see that suggest that there's local sources of low energy cosmic rays in those clouds. Isabel and I have been looking at more detailed cosmic ray models. For the first time, we've been able to run simulations in the recent past that actually follow the full spectrum of cosmic rays from sort of MeV to greater than TeV energies and follow multiple species, all dynamically on the fly, which allows you to do things that you could never do with codes like galprop and things like that, because those assume things like a homogeneous, static, time-steady ISM, which aren't true on large scales in the ISM. And compare those to things like Voyager and AMS spectra. And another student who's defending this year, Sam Panada, has built synthetic pipelines to translate constraints on magnetic fields and cosmic rays into observables like Faraday rotation and synchrotron maps, synchrotron spectra of galaxies, synthetic synchrotron halos, synchrotron polarization, et cetera. And there's a lot of really cool results coming out of that, telling us things like why certain classical sort of theoretical models of cosmic ray transport either can't work or probably aren't what nature is doing in certain environments, as well as things like how we interpret some of the synchrotron data may be wrong. You know, not totally shockingly to many people, when you traditionally interpret synchrotron data, you make a lot of strong assumptions like equipartition between magnetic fields and cosmic rays, and that cosmic ray spectra and electron to proton ratios are identical everywhere else in the universe as they are to what Voyager measures, et cetera. And those assumptions aren't always good. And that can bias you by orders of magnitude in some cases in your inferences about these things. But you might notice, if you're thinking about what I showed previously in my slide, where I showed the circumgalactic medium confinement, none of these constraints constrains the circumgalactic medium. These are all coming from the relatively dense ISM, right? And that's where we actually have all these constraints. So if we want to actually ask about those exotic environments, the problem is if I just extrapolate different theoretical models, I can get anything in those environments because the theory is so uncertain. A couple different models we played with gave something like factors of 10 to the 10 different values of the scattering rates for cosmic rays in the CGM. So we really are starting to think about, you know, going beyond that. So Sam in particular, in collaboration with Irina Butsky, has been thinking about how to use a combination of things like Faraday rotation and dispersion measures from FRBs through the CGM, CGM pressure constraints from things like UV absorption lines weighing the CGM in different systems to constrain what's really allowed in terms of cosmic ray diffusion coefficients and in those different environments. These are more indirect, but that's what we have to work with because we just aren't going to put a cosmic ray detector in the CGM anytime soon. I could give similar anecdotes or interesting highlights about a number of other projects that I don't have time to. Of course, there's similar questions that we're working on in our work on galaxy formation. Folks like Matt and others in FIRE continue to work on a lot of interesting topics on modeling small scales with these FIRE simulations. Folks like Isabel and recent former student Jacob Shen are continuing to work on a lot of interesting problems, some in collaboration with Mariangela and others here on testing different particle dark matter models, looking at how those affect large scales. Folks like Mike are continuing to develop projects like StarForge, simulating the smallest scales of star formation where we resolve individual stars. And a number of the projects I mentioned by Nadine were using the StarForge framework for that. So there's a lot of exciting stuff happening on all of these. I'm going to spend the rest of my talk talking about one more example of small and large scales talking to each other, which is black holes, specifically massive black holes in galaxy centers. Now, we don't need with this audience to motivate that these things exist. Here's just our beautiful animation of the stars around the galactic center, literally Nobel Prize winning work. And of course, we have other really amazing observations like EHT's map of the plasma right around the event horizon of M87 and Sag-A star. And of course, we've also known for decades that these black holes must exist at the centers of galaxies because they power some of the most luminous and interesting objects. Well, interesting is my interpretation, but in the universe, things like quasars and Seyferts and radio galaxies, where we see things like these beautiful jets going out to large scales. But these also highlight the challenge I'm talking about because, of course, the size scale of the event horizon, where, for example, we think most of the power of this jet is being generated, is of order in AU. Whereas we see this thing going out to and affecting the medium out to megaparsec scales, basically, in the most extreme cases. So it's clearly an intrinsically multi-scale problem. It's also an intrinsically multi-physics problem. Because if you want to do this range of scales, it's not just about resolution, it's about physics. And the physics approximations that you can make, or the physics that matter most on these different scales, are different. And there's some physics that are hard to do that matter on all of these scales that are listed here. And as a result, some of the really zeroth order questions in our understanding of supermassive black holes remain unanswered because these are hard. And that includes, what do I mean by zeroth order questions? Where do they come from? What are the seeds, so to speak, of the supermassive black holes? How do they grow? How do they actually accrete? And how does that depend on the environments that they're in? And what do they do to their surroundings? What we call AGN feedback. So I'm going to address each of these in turn, although I'm only going to briefly touch on the feedback question. And I'm going to start for each of them by bringing up a couple of points of conventional wisdom that in some cases I was taught, in some cases I think I contributed to that conventional wisdom that I don't think are true, at least anymore. So when we think about seeds, one piece of conventional wisdom I hear said a lot, although I think some people here will disagree about whether it's really conventional wisdom, is that high redshift supermassive black holes, these really massive things we're seeing at very early times, require some mechanism like direct collapse. For those who aren't familiar with that, that just means skipping the queue entirely and going straight to supermassive, basically, as opposed to accreting from a small black hole to get to supermassive. Another piece of conventional wisdom you often hear repeated is that black holes will somehow sink to galaxy centers and then grow. And in fact, we often include subgrid models to force them to sink to galaxy centers because we assume it should happen if we just had enough resolution in our simulations. But I'm going to argue both of these are wrong. So on the direct collapse point of view, the motivation for that argument, you need these giant seeds, is basically up here. If you see a really massive black hole early in the universe where there hasn't been much time, you have two options. And this is explained by this equation, which says the black hole mass versus time is given by some initial mass times this function, assuming you're accreting at some fraction lambda ed of the Eddington limit. So this is your accretion rate relative to Eddington, right? The standard upper limit for an isotropic, optically thin, luminous object. And this is your time that you've had to accrete. So in the early universe, you haven't had a lot of delta T, basically. And we see big M black hole. So you've got two options to explain big M black hole at small delta T. You can either have very heavy seeds, which is like the direct collapse scenario, or you can have super Eddington accretion here. Now, the really simple argument for why I like super Eddington accretion is that lambda's inside an exponential here, m initial is outside an exponential. So it's a lot easier to get a big number by putting the thing inside the exponential. And just to quantitatively show that, if you assume that no matter what you do, you're still limited by the Eddington limit, here's how little you gain by using supermassive seeds. If you start from a black hole we know nature can make at 100 solar masses, let's say, we see those from LIGO, and ask how long will it take me to get to, say, a couple billion solar masses? It'll take me about 800 million years accreting at the Eddington limit. What if I skip the queue and jump to the lowest mass supermassive black holes, 100,000 solar masses? Well, I've chipped off only 300 million years. It still takes me 500 million years to get there. That's actually not that much of a gain. On the other hand, what happens if I say 1% of the time, these things have a flash of accretion that's at 1,000 times the Eddington limit? They're hyper Eddington accretors. Well, then I can do it in a mega year with whichever seed you give me. So that's a big difference, basically. That's the inside the exponential versus out. And I think, as I'll show, physically, we're seeing in the theory more and more ways to do this, basically, to achieve these very high accretion rates. And we've looked at this. So a recent student, Yanlong Shi, who's now a postdoc at CETA, and a postdoc, Kyle Kremer, who's just started a faculty job at UCSD, looked at this in a series of papers, looked at both seed models and accretion models, and found that even very low mass stellar mass seeds could undergo episodic periods of hyper Eddington accretion if they were in sufficiently dense environments, things like starburst nuclei of galaxies. These are extreme environments, to be clear, very dense, very massive. These are not the environments of the gas floating around your typical top 3 star right after it explodes. These are not going to transition to giant masses after that phase. They're going to happen much later on when the potential well of the galaxy is much deeper and you're able to bring in a lot more gas and a lot higher densities. And then your random seed can encounter that gas and start accreting incredibly rapidly, basically. But it is at least viable to do in those environments. We have also looked at more exotic seeds. Yanlong looked at things like runaway stellar mergers and some other mechanisms and found they generally weren't that good at giving you very massive seeds. You could get there. There's a paper by Jacob Shen and collaborators. If you're willing to invoke beyond standard model physics, I can give you some ways to skip the queue entirely and go straight to billion solar mass black hole through things like exotic dark matter mechanisms. But, you know, your prior should always be, that's a, you know, a big reach there. But in the process of looking at this, I think something that we and a number of other groups have seen is that there's another problem that's been less appreciated in this area of getting seeds to grow. And it's related to something that's become a really important part of our understanding of galaxy formation, which is that galaxies ubiquitously undergo an early phase of evolution where their star formation is very bursty and the galaxy formation process is very violent and clumpy and disordered and turbulent and messy. And you see that in this movie showing the gas in a Milky Way mass galaxy. At high redshifts, it was just a clumpy nightmare, basically. And that's because gas inflows are very rapid. Things are cold accretion. Mergers are happening quickly. The galaxy is gas rich. So it fragments into large clumps that themselves excite strong star formation, which gives you feedback that blows everything out, et cetera. And then eventually it settles down. And it's only in this particular simulation after about redshift 0.7 that it starts to calm down and actually look like the textbook story of galaxy formation that at least I was taught in grad school, which is that you have a nice hot virial shock as gas flows into the halo that then gently cools, conserving angular momentum, and circularizes as it cools to wrap up and form the outer edge of the gaseous disk. And that does happen at low redshifts here. And that's sort of the transition between this clumpy, messy phase and forming these beautiful disks. These are some of the simulation disks at z of 0. And that transition was predicted in a number of simulations. This is some work by Anna Yu showing that that transition between bursty and thin disk, the bursty to smooth transition was closely related to the formation of the thin disk of the galaxy. And now I think there's been a lot of excitement with data from Gaia and other surveys showing that this was really borne out in galaxies like the Milky Way, this transition, and it's really important for understanding of thick disk formation. Jacob Shen and others have shown that this could also be really important for explaining a lot of the properties of the JWST galaxies and their UV brightness if they're still in this very bursty phase, for example, with highly fluctuating star formation rates. But it is a real problem if you want to get black holes to grow really fast, basically, because in this churny, bursty environment, everything's just flinging all over the place. Your black holes can't dynamically settle to the center. Heck, there is no dynamical center of this galaxy, and the gas is flying every which way, et cetera. So you bounce around, you don't sink to the center, you often just get flung out of the galaxy entirely. In fact, and Linhao Ma in a couple of papers showed this very nicely. And there's a couple ways out of this. Either you could form your seeds very late after this dynamical settling process happens, but then you've got other problems, or you could do something like anchor your seed black hole in a safe space by having something like a very massive star cluster be the natal location of those seeds so that they're protected from this rough environment. And then they can sink to the center, not on their own, but with that massive star cluster. And indeed, Yanlong Shi, whom I mentioned earlier, looked at some simulations where we did a wide survey of different parameters of clouds and star cluster formation and found some interesting examples that he wrote up in a neat case study that combined a lot of these ideas, all exhibited in one simulation. So the idea was you have some gas complex that is going to collapse and turn into stars. Most of the time, it follows this track. If the cloud is low density, low mass, if it's a small halo, if it's if it's too metal poor, if it's not able to cool fast enough, basically you might form some stars, but stellar feedback will win and blow up the cloud. And a number of people, including Mike and others, have shown that this is the sort of more typical cloud's fate, is to blow up the medium around it. But if you have the right conditions, you get a different channel, okay? So if you're dense and massive enough, you can trigger an entirely different channel if you have a bunch of low mass black hole seeds lying around. So if you're dense enough, again, folks like Mike showed that your stellar feedback will be unable to resist the force of gravity in the cloud, and so you'll get runaway star formation and turn an order 1 fraction of the mass of the complex into stars. And so it'll collapse and fragment very rapidly. And so in this plot, you see the mass versus time, in this case of the stars, in this case of the black hole seed. So the mass of the stars shoots up as this thing starts forming. During this very rapid collapse phase, because the stars aren't able to blow out the dense gas, occasionally your little seeds will get lucky and hit a dense gas clump and accrete in little jumps, potentially at highly super Eddington rates, but they're not going to get hugely massive doing this. But also during this process, and this has become sort of the I'd say more standard paradigm of how we understand star cluster formation these days, you get this interesting hierarchical star cluster formation process where your cloud actually breaks into many different subclusters, which collectively have a very high cross-section for capturing any seed black holes that are wandering around, or at least a fraction of the seeds, the small black holes that are wandering around. They get captured by these subclusters, and then the subclusters, because they're all mutually bound to each other in this parent cloud, merge together very quickly in of order 1 dynamical time, because it's sort of a series of major mergers of clumps that are right next to each other. They merge together into one sort of supercluster, basically. And the nice part about that is they both protect the black holes, but they very quickly shuttle those black holes to the very center of this newly formed natal superstar cluster, let's call it. And this superstar cluster has the properties of things like superstar clusters, dwarf nuclei of dwarf galaxies that we see, something like Here's the numbers from this particular simulation: 100 million solar masses and a couple hundred kilometer a second velocity dispersion in the star cluster. So the black hole is anchored in that, brought to the center. Any remaining gas is trapped very effectively by that now deep potential well of the stars, not just the black hole. When the black hole was wandering around accreting Bondi-Hoyle style on its own, it's very bad at grabbing a ton of that gas because it's just not massive enough at the early stage. But now that star cluster potential can shuttle everything in, and it forms, in this case, a few parsec size accretion disk, which happens to be hypermagnetized, which I'll talk about in a moment, and leads into my next section, a special kind of accretion disk that enables it to grow at super Eddington rates, which is the ramp up phase here that you see, until this thing gets to something like 1 million solar masses at the end of this. It also just happens that at the end of that particular simulation, this young cluster, while it's towards the end of its accretion, has a lot of properties that look a lot like a little red dot. So we're trying to look at that in more detail. So this is a cute story, but there's a lot of work that needs to be done to see if these pieces really work, let alone what the predictions really are for the demographics and details of this. But it leads very naturally into what is that accretion disk, and I'll come to that in just a moment. But before I do, I want to come back to these points about the seeds. So I said high redshift black holes require direct collapse. Well, they actually don't if you can have super Eddington accretion. And in fact, if you have super Eddington accretion, the seed masses stop mattering to first order. Likewise, this conventional wisdom that they sink, well, they really can't sink unless either these very well-defined dynamical centers have already formed in galaxies, or again, they're anchored in something like natal massive star clusters. So what about their growth? So let's assume that we get through that stage and we've got a black hole, it's anchored, it's got gas potentially around it. How do they actually grow? We know that most of the black hole mass in the present day universe, supermassive black hole mass, was assembled from gas accretion, okay? So what are some pieces of conventional wisdom there? There have been challenges for decades to our understanding of how black holes accrete a lot, basically, especially high accretion rates. So for example, people have worried for a long time that fueling from galaxy scales becomes very inefficient at what we call the black hole radius of influence. This is just the radius where the black hole starts to dominate the gravity, the potential, which is like a few parsecs in a typical galaxy. We also have people have argued for decades that if you try to fuel a black hole at super Eddington rates from large scales, before you get into the final accretion disk, that the gas will get too dense, it'll form stars way too rapidly, it'll fragment catastrophically into stars, and the stars will eat everything before it can get anywhere near the black hole, basically. And to some extent, these are predicated on the following, which is that we usually assume that the accretion disk is something like these traditional disk models going back to the 1970s, Shakura-Sinyaev, Novikov-Thorne, these alpha disk models. And the key assumption by which I'll refer to traditional accretion disk models is that they have weak magnetic fields. There are exceptions to this in the past, I want to emphasize, but that's generally been the standard reference that we've assumed. So how do you go about this problem? Well, we want to look at how black holes actually get their gas. Now, this is a non-trivial question, and it does not have one answer. Been to conferences with this as the conference title, where people argued all sorts of different things because it's a multi-scale problem, basically, right? So here's an illustration of gas and stars on the range of scales. The gas that black holes accrete is ultimately coming from the cosmic web on megaparsec scales before it makes its way finally to the black hole. And so there's a range of scales, and the question of how you feed the black hole, which is often asked in different papers, depends on what range of scales they're considering, right? The answer to that. And some of these, I think we've made a lot of progress on understanding. So for example, how does gas get from the intergalactic medium into galaxies is really what this large scale is asking about. And there, I think we've made a lot of progress understanding things like the cosmic web and how you have cold accretion over filaments and the whole hot versus cold accretion, how different instabilities modify accretion on the galaxies, et cetera. Then inside of galaxies, how does gas get from the galaxy scale to the bulge, let's say? Well, there's ideas that have been around a long time about things like galaxy mergers, which can very efficiently torque the gas and cause it to fall into the center, as well as things like disk instabilities, bars and spiral arms that we know can efficiently remove angular momentum from gas. And I should emphasize this problem is really an angular momentum problem because you have to decrease the angular momentum by a factor of something like 10 million to go from a typical parcel of gas falling into the virial radius of a galaxy to get it into the event horizon of the black hole. What about on smaller scales inside the bulge? Well, there's ideas going back decades as well there. Most famously, sort of Begelman and Schlossman coined this phrase of bars within bars, that you have a hierarchy of instabilities that occur. And in fact, that seems to be borne out in simulations. When I worked on this in my postdoc, we tried to sort of rename this stuff within stuff because it's rarely bars. It's a whole host of different non-axisymmetric modes. But modulo that, you basically see this process iterate. Now, some of what I described about what happens when you hit this radius of influence at a few parsecs, some of that conventional wisdom that you can't get through that radius comes from the fact that a bar and a lot of these traditional galactic instabilities, you can show that those modes can't propagate into a Keplerian potential. They basically, things like the bar will just reflect off of that potential or off of that radius. However, we do know of non-axisymmetric instabilities that propagate through that radius just fine. There's a subclass of m=1 modes, slow m=1 modes for those more interested in the dynamics that, for example, have no problem propagating into a Keplerian potential. They have no inner Lindblad resonance in a Keplerian potential. The mode can propagate all the way to r=0 formally. So this can actually continue uninhibited all the way through. Especially efficiently if you have a two-component disk of both gas and stars at these radii. I'll come back to that point in a moment. But then you really get, when you get to sort of sub-parsec scales, is where you suddenly get a big gap, where there are exceptions, but there's been very little work on this range of scales compared to these much larger scales, or compared to much smaller scales, where you get, again, the great body of work on more traditional accretion disk simulations near the horizon, where you measure, say, the distances in units of gravitational radii or event horizons or Schwarzschild radii. But typically, these simulations might go out to like 100 gravitational radii. This to this is something like a factor of 10,000 to 1,000,000 difference in scale that we're missing here on this plot. I haven't drawn the vertical axis to scale really here. So why is that range so poorly understood? Well, again, it's not just dynamic range, it's the physics. The problem is the physics approximations that you can make in your accretion disk simulation are very different from what you can make here. So here you might need to worry, you definitely need to worry about MHD, you might need to worry about GR if you're going all the way to the horizon, you definitely need to worry about radiation pressure in the disk at high accretion rates. But your cooling, for example, often is ignored entirely or treated with a very simple, fully LTE, single temperature, black body radiation transport assumptions, because you assume everything's super optically thick and thermalized and stuff like that. Here, you absolutely can't do that. You usually assume the opposite limit, optically thin, cooling radiation just escapes to infinity everywhere. And you have things here that you worry about, like self-gravity and star formation, that you don't worry about ever on these scales, for example. And until very recently, there haven't been codes that could do both scales at the same time, basically. Briefly, to build up to that, let me say we've been getting better and better at linking these scales. I showed a patchwork of simulations, and that's been much of the work for the last couple decades. But we've been getting better and better at linking these self-consistently. So a lot of this work in FIRE was led by Daniel Engels-Alcazar, with some more recent work led by Jonathan Mercedes-Feliz and Rachel Cochran, where they took our cosmological simulations and used a sort of adaptive refinement technique to just keep zooming in to smaller and smaller scales following gas flows during interesting phases of evolution, all the way down to sub-parsec scales around the black hole. And they stopped at sub-parsec scales, not because we couldn't numerically go further, but because, again, the physics at the time in the code did not make sense to go further. But nonetheless, they were able to show that you could get a wide range of accretion rates into, say, a few tenths of a parsec of a galaxy, depending on the local gas conditions, things ranging from sort of relatively modest AGN to 5, 10 solar mass a year booming quasar level accretion rates. And how does that work on these larger scales? Well, just very briefly, usually when you have these larger scales, your accretion is given by these sort of gravitational torques. This process is very well understood on galactic scales for star formation and things like that, but it can just iterate all the way down to a certain extent. And this is basically maximally efficient when you have a disk of stars and a disk of gas that are aligned with each other, as usually happens on galaxy scales. And the idea is that you have some perturbation like a bar or a spiral arm, and your gas and stars will not move at the same exact pattern through each other, basically. So for example, you have a stellar disk with some gas, the stars fall into the overdensity of, say, the bar in the stars, and they get accelerated, and then they try and come out the other side and they get decelerated. So gas slams into the other gas. The gas that's coming through later slams into the gas at the front. You get a strong shock. These shocks are radiative, so that you get a big jump in density. And we see things like molecular cloud formation and rapid triggered star formation at the leading edge of spiral arms. And this is a standard thing that we've tested observationally and is seen in lots and lots of numerical models. But it also means that you get very efficient dissipation and angular momentum loss. And it's important that you do the nonlinear calculation because, for example, we showed in some papers 10, 15 years ago that if you take the Fenian-Tremaine or these famous calculations by Lyndon Bell and Kalnas and others, you get that these torques are incredibly inefficient, basically. And the problem is that the standard textbook calculation says these torques are incredibly weak and really only can possibly operate near resonances. But that's because they're doing linear perturbation theory, so they don't include the full effect of things like shocks that disrupt this process and really are very important for this. But the problem is, eventually on small scales, you run out of stars to strongly torque your gas and generate these shocks, for example. And you kind of have to stop forming stars at such a prodigious rate on small enough scales, or else you would see nuclear stellar densities far in excess of what we actually observe. So what happens there? Well, to do that, to go to these smaller scales, we need to push further, and that's been our goal with this forged in fire set of simulations that the first results came out about a year ago. And this is taking our fire simulations on large scales, but linking them to the Starforge simulations that, again, folks like Mike Grudich, along with others like Stella Offner and David Yusenyov and Anna Rosen, built to follow dense gas in GMCs all the way down to the scales of individual stars and protostellar disks, much higher densities with self-consistent radiation transport, et cetera. Lots of physics all then put in as you zoom into small scales in this problem, a list of which are here. But what we can get from that is the ability to sort of self-consistently in a single simulation zoom through these scales. So what is the movie you're looking at? Well, it's a density projection of a cosmological simulation where we keep zooming in following the gas during an accretion event into the central, initially tens of parsecs in this galaxy. And let me start it again. So you start on these very large scales. This galaxy happens to be a redshift, say 4.5 massive starburst galaxy. It's forming stars at a couple hundred solar masses a year. And there's a giant massive gas complex of something like a 10 to the 8 solar masses that gets knocked on an orbit near a pre-existing 10 million solar mass black hole and gets tidally torn apart near the tidal radius of that black hole. And as you get closer, you can really see the tidal debris from this. And you get this tidal tail that's ripped off from the cloud, which is bound and eventually gets some of that that's stolen gets wrapped up and circularizes to form the accretion disk around this black hole. And as we get to small scales, you really beautifully see there's clearly an accretion disk there. And this simulation went down to something like 80 AU around the black hole. And as I'll show in a moment, we've now gone even further with these simulations. And again, the physics is really important here, including sort of all of these physics like multiband, non-LTE radiation coupled to the thermochemistry in order to be able to self-consistently treat this range of scales, for example. And here's another illustration from some work that should be coming out in the next couple months, where we push that further and go all the way to near horizon scales in the same simulation. So this final simulation goes to sub-AU resolution around the black hole and follows the gas all the way down to the ISCO. Here it's colored by the phases of the gas. You can see multi-phase structure and things like that at various radii around the black hole, which itself is super interesting as well. And a paper that came out on arXiv today by Nick Kaz you might worry, the one thing I don't have in that panoply of physics is GR. This is not a GR code. So you might worry approaching the ISCO, and you should, that that's not valid to do. So Nick just took the inner region of that simulation, mapped it into his code, Hammer, and ran it, which is a GRMHD code, and ran the inner disk there using essentially our simulation as an outer boundary and initial condition, where you can go all the way to the horizon and see things like jet formation happening in this simulation. I encourage you to check it out. But perhaps the most exciting thing to come out of all of this is the actual structure of these accretion disks is wildly different from what we had anticipated. We were sort of prepared to call, the goal of this project was to get to seeing that an accretion disk formed, right? That was the goal. We expected it to be a sort of standard accretion disk. What we did not expect is that this accretion disk would have properties wildly different from the standard model of accretion disks, and most notably in that they are much more strongly magnetized than that standard model. So quantitatively, what do I mean by much more strongly magnetized? This is a wedge plot showing profiles of different quantities. The important thing is simply that the magnetic pressure is much larger than the thermal pressure basically everywhere, the gas thermal pressure everywhere in the disk. The turbulence is of order the magnetic pressure, meaning that you sort of have transalphanic turbulence, which means because the thermal pressure is weak, you have supersonic turbulence basically everywhere in the disk. And in the outer disk, the magnetic pressure is much larger than the radiation pressure. For the version accreting at super Eddington rates, the inner region, the radiation and magnetic pressures are comparable to each other. We now have a run that's significantly sub-Eddington, where it's the radiation pressure, as you'd expect when you're much below the Eddington limit, is not important anywhere, basically. But I just then want to spend the last bit of the talk talking about why are we getting these magnetically dominated disks? So where did this come from? Why did this happen in these simulations? To do that, let me first explain what we traditionally assume in most of, but by no means all of, the accretion disk modeling literature. So generally, when people are modeling accretion disks, especially numerically, you start from an initial condition like this. You don't know what's happening at the ISM. You're not connecting it to the ISM. You start from a sort of ad hoc initial condition that's usually in hydrostatic equilibrium. It's often these tori that are hydrostatically supported. So let's just look at sort of edge-on wedge of that torus. You've got this gas that's hot and supported. It has generally either you initialize it with trace magnetic fields, and you want to ask how do the magnetic fields get amplified as I evolve this disk, or you might initialize it with a strong vertical net field that laces the disk. And that can be motivated for several reasons. It might be a very good initial condition if you're studying a disk around a neutron star, for example, with the dipole field of the neutron star. The point is, in either case, as this gas cools, gravity is going to pull it down towards the midplane, and it's going to collapse to some thin configuration until it builds up enough thermal pressure to resist gravity in the vertical direction. Now, I want to emphasize that in the outer disk, these disks get really, really thin in this model. So the aspect ratio is something like, whether you assume it's a Shakura-Senyaev disk or like a Sirko and Goodman disk or something like that, you're talking about aspect ratios of like 1,000 to 1 in the outer disk. Okay, so these are like paper thin disks, relatively speaking. Now, once you get super thin, you have something like the magnetorotational instability that is able to take these magnetic fields, amplify them, generate some effective turbulent Maxwell or Reynolds stress or effective viscosity, and that transports angular momentum and allows the disk to accrete inwards. But it does so very slowly. The traditional accretion is a very secular process in these models. It takes typically something like millions of orbital times for the gas to lose an order 1 fraction of its angular momentum. Now, we've known for a long time that this model alone is clearly not what nature does. It has a lot of problems. So there's a lot of issues with this. So for example, these models in the outer regions are wildly gravitationally unstable. The tumor AQ parameter is less than 10 to the minus 6 in the outer disk. That's the origin of this claim that it should fragment catastrophically before you can get to the center. There are other instabilities at high accretion rates that have been known about for a long time, thermal and viscous instabilities that we don't really see evidence for. Empirically, they have all sorts of issues with their spectra. So even the thin disk itself, there's a long-standing issue that this model predicts the disk is generically too hot, that it should peak. The big blue bump should peak more like in the much shorter wavelengths, because it should have an effective temperature that's nearly 1,000,000 Kelvin. And you also don't have things that we know should be there that are reprocessing the light to explain things like the soft excess and other components we see. And also there's microlensing and other observations indicate that these disks are too compact in their emitting regions compared to what's observed. And in particular, there's all this other stuff that we know has to be there. So what do I mean by other stuff? For AGN people, this is familiar. Everybody who works on AGN has seen a million versions of this cartoon. Half the people, if you're a senior person in the room at some point working on AGN, you may have had to construct your own cartoon, where you've got things like the dusty torus, the broadline region, some Comptonizing medium that explains the soft excess, the corona. These all explain things that we know are there. We see them in the spectra, and you know that they cannot come from the thin disk. The broadline region, just the geometric covering factor alone that it needs to subtend on the sky, let alone its densities and temperatures, mean there's no way it can be part of this super thin Shakura-Sunyaev disk, okay? And usually in the cartoons, they're just kind of phenomenologically there, hovering above the disk. And the question is, why are they hovering? What's getting them up there? And there have certainly been ideas about that. What's floating them above the disk, but it's a challenging question to self-consistently model that. So what's happening differently in these simulations that I just described? Well, the key is that boundary conditions for this problem really do matter, okay? And the cartoon I'm going to illustrate was shown before these simulations. This is nice work by Yuri, for example, with Gabrov and Levin showed in simulations, for example, of cloud being disrupted by a black hole, a lot of the things I'm going to illustrate now that are very similar to what we see in our galaxy zoom-in simulation. But the idea is you have some galactic ISM that's coming in and being tidally grabbed and wrapped up by the black hole. That galactic ISM might have a pre-existing strong toroidal field like our galaxy, or it might just have a completely tangled magnetic field. That's fine. So this tangled field, though, when you wrap this thing up tidally, will get tidally stretched and become preferentially toroidal and azimuthal and wound up in that direction. And that's exactly what we see in the simulations. These are sort of the filaments falling in and wrapping up around the black hole in the simulation. And here's an illustration of the magnetic field lines on large to medium to smaller scales in the black hole. And what you see is they go from more disordered on large scales as it's falling in to getting wound up tighter and tighter and more azimuthal as you move in towards the disk. And now this has been seen in other simulations using different codes and numerical methods and assumptions as well. So Yanlong in the simulations I mentioned earlier saw this from IMDHs accreting from gas in molecular clouds. Minghao Guo at Princeton had recent papers looking at accretion in sort of M87 type galaxies, where under conditions where you had dense clouds fall in and occasionally give you a big disk, you get this wind up. There was a paper, I think, 2 days ago on Archive that I just added here, Luo and Schlossman, who saw a similar disk form in a simulation of a magnetized accretion disk around a sort of metal-free protostar that they were modeling. There's some work by Yash Tomar, a student at Caltech, on other situations that we're seeing these disks form in as well. So what happens if we now look at the process of the sort of settling of this disk? So let's look at our edge-on cutout again, but now we have this strong toroidal field threading the disk. Now, that disk initially has a plasma beta ratio of magnetic to thermal pressure of order 1, maybe a little less than 1, just because this gas is cold. We know that. This is atomic molecular gas from the ISM. That's observationally very easily got beta less than 1, and we see that all the time. So what happens when you try and compress that disk under gravity? Well, it's got these pre-existing magnetic fields. Now you're squishing the magnetic field lines together. They resist your collapse and they halt that vertical collapse while the disk is still quite thick. And they get their magnetic pressure amplified. And critically, you halt this collapse process long before you ever reach the sort of super thin disk state. And that's really key because part of the reason, it's not by any means the only reason why I think some of these older simulations didn't consider these kinds of initial conditions is because if you start from a trace field with a super thin disk, you will never amplify it to reach this state, okay? You can't do it. Energetically, you just can't do it. You've already lost. Gravity has won and crushed your disk down to such high densities that to amplify B so much to throw it back out, it just doesn't work, basically. There's no budget to do it. On top of that, these strong magnetic fields mean that you get very strong Maxwell stresses that provide very rapid accretion, basically. So the accretion time is measured in sort of order ones of orbital times rather than order millions of orbital times in this case. So it's not a secular process at all anymore. And that's important because it means the gas will rapidly flow in, but it also means that you can sort of rapidly replenish the magnetic field in these disks from the magnetic flux coming in from larger radii, potentially. And that may also be important for driving the turbulence and explaining a lot of properties of these disks. Now, there's a lot of detailed questions that are remain to be answered about this, about what's the structure of the torques, how does the field replenish itself, what's the role of Parker instabilities, are they purely removing flux or can they even drive a sort of dynamo? Is there a dynamo at all in these disks or is it just advection? What's driving the turbulence in these disks? These are great questions. I think in my conversation with Yuri earlier, he cut it off by saying we could talk about these till the cows come home, but they're really good questions and they're not, I don't have simple, clean answers for that. We're trying to study that. There was a recent paper by John O'Squire looking at idealized simulations. We're trying to get a better handle on this. The downside of these massively multi-physics global simulations that it's very hard to tease apart these different types of mechanisms and things like that and really understand those small scale physics. So definitely more work needed. But in the last few minutes, let me just say, why do you care about this? Well, if you care about AGN, this should already be very exciting. But even if you care about AGN only in the most indirect sense, this has a lot of important consequences. So some of the differences between these disks, so I said, okay, magnetically dominated versus not, thick versus thin, I already highlighted. Strongly turbulent versus effectively laminar with weak turbulence is another key consequence. That also has the effect that these magnetized disks are effectively always multi-phase in the disk, whereas alpha disk is essentially by construction uniphase. I mentioned the very weak versus strong stresses. That in turn has enormous consequences for the disk mass because the disk has such strong stress here. For a given accretion rate, if you want to explain a given observed accretion rate, you have a much lower mass in steady state in the disk because it takes a few orbital times to accrete instead of, if it takes 1,000,000 orbital times to accrete, you have to pile up a lot more mass in the disk to get it to accrete in those models, which in turn has a huge effect on the gravitational stability of the disks. These disks are always gravitationally stable inside of the circularization radius of the disk, whereas the others were very gravitationally unstable. Also, that thickness has huge consequences for things like the radiative transfer out of the disks, because light traveling out of these disks intercepts the outer disk and gets reprocessed. You have essentially a giant photosphere covering most of the sky. So there's a lot of very complex self-illumination and things like that that you need to take into account that changes the thermal properties and radiation properties of the disk. And let me just give you a quick example of how dramatic this is. So I can take this simulation and turn off magnetic fields. And what do I get? Well, it immediately collapses to the sort of thin disk model that it should. But it also means that my star formation rate in the inner disk jumps by a factor of 100,000. And that throttles the inflow into the inner regions. It was dropping here, it dropped by a factor of 1,000, and it was dropping more as we ran the simulation, but it was getting too expensive because there were so many stars forming in the central region. These multi-phase structures also have really important observable consequences potentially. I've gone too long without showing a movie, so I'll show a movie to highlight some of them. So here's just highlighting some of the different pressures in the disk, same fall-in animation, but now showing like where your thermal pressure dominated, where you can see hot gas filling some of the volume on much larger radii, where your sort of cold gas that's turbulence dominated, that's not so strongly magnetized, and where you're purely magnetically dominated in the disk. You see you get more magnetically dominated in the inner region, but you can still see interesting little cloudlets. They're a little hard to see in this screen, but you can still see cool little cloudlets and things like that that have different pressure in them. And so modeling all of this is challenging. There's a student, Jaden Bardati, along with a student from the observational side, Hazel Yun, who's collaborating, trying to model the radiative transfer on these disks to actually make synthetic SEDs and ask, do these really look like real quasar spectra? We think that they qualitatively have the right properties you need. So for example, when you calculate the properties of the sort of surface of the disk at 10 to 100 light days, this is plotting Z over R versus R, just with a cartoon showing what the phase structure at different radii typically is. So light from the inner disk is sort of traveling on straight lines to the outer disk here. A lot of it's going to hit this. So you're going to get things like hot dust from the inner edge of the torus. There's a section here that's sort of got densities and temperatures all in the range that are canonically the broadline region properties, sort of 10 to the 10 particles per cubic centimeter, 10 to the 4 Kelvin, optically thin surface layer of gas that's multi-phase and clumpy, and be really cool. I think it would be the first time a simulation has self-consistently produced a broadline region if we can actually see that emerge. Or maybe we'll see something that looks nothing like observations emerge and we'll know that nature doesn't do this. I don't think that's what's going to happen, but Nick's paper also had a very preliminary comparison using the in-code radiation hydro. He just calculated what's the sort of surface of emission for the escaping radiation, and this is the fraction of radiation that escapes from a given surface. So where this is about a half, you can think of as the effective size, apparent size you'd see of the disk. And these vertical lines are microlensing inferred sizes of disks with the same bolometric luminosity as in Nick's simulation, and plausible, but you know, early days. There's a bunch of other things to ask. So with Dalia Baron and Asha Piotrowska, we're trying to look at, are there dynamical constraints on things like the masses of the disks that you can set? So this is a hypothetical plot. The idea is, you know, if you have a very massive outer disk, like some of these other models, like a Shakura-Sunyaev model predict, where the disk is so massive at large radii, it should actually perturb the kinematics. And we know from things like maser motion around disks that often it has these beautiful Keplerian motions. So that actually lets you set very strong limits on the mass of the disk. And again, these are not real data. This is the proposal plot, right? Where this is what we're hoping to do here. But all right, so this is very exciting. And to summarize our conventional wisdom, the point is that fueling from galaxy scales becomes inefficient. Well, we said that fueling becomes inefficient, but in fact, it's extremely efficient at these large scales. We said that super Eddington fueling can lead to runaway fragmentation, but in fact, super Eddington fueling can be fine if you have the right type of disk, but that right type of disk is not something like a Shakura-Sunyaev disk, but can be magnetically dominated. Now, I was, not shockingly for anybody who knows me, I was too ambitious to even think I'd spend a minute on black hole feedback in this talk. So I'll skip through this, but I just want to show sort of one slide showing a diversity of what we're working on. What I just wanted to highlight is the next question to ask for feedback is really, now that we've been able to follow these flows in, what comes back out? Right? Can we start making some of the first self-consistent predictions from going back out to large scales from these small scales for what black hole feedback should look like and what should it do to the galaxy? And that's a challenging question because we have to both, you know, in the simulations do things like zoom back out now that we have this, because we can't evolve, you know, the time step in Nick's simulation at the event horizon. This was the first simulation I've ever been involved in where it took more than one second of wall clock time to advance the simulation a second of simulation time. And so you can't run that for 100 million years to see what it does to the galaxy, it turns out. But we can zoom back out with, say, a subgrid model adapting the boundary conditions from this simulation. And folks like Kung-Yi Su, who's at the Black Hole Initiative, working with Hyerin Cho, have been adapting new numerical methods to do this. And he's written a number of papers on what jets do. Because the other question you want to look at is, there's many different types of AGN feedback. There isn't one number. There's no, I'm the person who wrote a lot of papers, not the only person, but I'm one of the people who wrote a lot of papers saying there's a magic number for AGN feedback. You need X% of the accretion energy and boom, feedback solves all your problems. But there is no one magic number because it really matters what the physical channel that the feedback is coming out in. These will have qualitatively different effects on the medium if the same energy comes out in jets versus cosmic rays versus radiation versus, sorry, this is impossible to see here. These are sort of slow non-relativistic winds here. It makes sense when the movie's playing and you can see it darker. But we've got different folks looking at these different aspects, trying to zoom back out and ask those questions on larger scales. Folks like Sam Bonata modeling the cosmic ray stuff that I mentioned earlier. Nadine's looking at some of the radiation pressure-driven winds, showing that they can induce new types of variability. Folks like Jonathan Mercedes Feliz and Rachel Cochran looking at these winds and how they sweep up gas on galactic scales. And we're just starting to make comparisons with things like elliptical galaxies using simplified subgrid models, because we're back out to large volume cosmological simulations, but trying to inform them from these small scales, where we can make, if you look at Lindsay Brin's recent paper, really reasonable ellipticals. The only problem is, here's the dirty secret, if you want me to make this and this, I can't at the same time. I can turn that into that and give you a lot of beautiful ellipticals or a lot of beautiful disks, but I still struggle to make the two at the same time, which of course nature does. And this is a well-known problem in understanding AGN feedback. So anyways, I'll end there. Thank you very much.
All right, well, thank you, Phil. We have run a little long, but I think we can have a question or two, and then there is a very nice reception right outside. So questions from the room? From the, yeah, press the thing in the...
I gave this talk at Yale and I was 50 minutes. I don't know where I...
We just encourage you to be relaxed and
yeah.
yourself, so it's a really nice talk. And I have a question, and maybe you said it and I actually missed it, but in the early discussion where you were talking about how one of the ways to get the seeds sort of to the center is to anchor them to a superstar cluster, and then that's massive enough that dynamical friction will operate to bring it in. Does that imply that massive superstar clusters that might become nuclear star clusters will always have an SMBH in them? Like, is that a necessary component, or is it possible to get a nuclear star cluster with no SMBH in it? Yeah.
So I think it's a good question. I think that it's hard to, so what I would say is it's easy in the simulations in principle to give you a nuclear star cluster with no SMBH, because you let me play with all the parameters for the seeding model and assumptions for the seeding. And of course I can make it as likely or unlikely as I want. That said, you know, thinking more physically about it, I actually think it is unlikely that you would get something that massive without picking up a decent mass, at least IMBH sort of level black hole, once you get to that big, right? But of course, one of the things this won't happen for every star cluster, or it will be so low mass, it won't matter. So if you scale this to like a typical globular, you're not gonna be talking about IMBHs in globulars. You might be talking about maybe this could get you up to 100 solar masses, which wouldn't even stay in the center of a globular, really. But yeah, that's my heuristic thought.
Julianne?
Yeah, so one of the things we do know about AGN is like they're not on all the time. Like in this model you're proposing, like do you have a sense about like what might drive the intermittency and the duty cycle? Like, are there ways that you can turn, like, you make a great case for why this happens, but we also need a way for it to stop happening.
Yes. Yeah, so we were just talking about this upstairs. I think there's definitely variability happening on all sort of time scales at the more usual, when we talk about variable AGN level. There might be some indications of some, full-on temporary shutdowns. The whole event in this case, because it's coming from this very massive cloud complex, is going to last for millions of years before that thing's gone. But intermittently, it could shut down potentially. We see some things where it sort of blows up the inner disk, where it gets arrested. It occasionally switches to more MAD-like configuration where it can maybe arrest, we were talking about. But again, we haven't really looked at the time axis as much yet. But it's a great question. And there are also things like, in Nick's paper, he sees some things like polarity flips of the jet. So the jet can definitely turn off transiently. But again, thinking about whether that can really match what we see I don't know yet.
So one of the things that like a thin disk model sort of arguably gets right is just you get a lot of UV from quasars. So if you really go to like this really extreme magnetic domination, do you have an understanding of sort of just how that works? Because then I guess in that model, really the energetics is sort of decoupled largely from the gravitational potential, right?
So you still get you actually, sorry, is this, oh yeah, I'm from Cleveland. Temporarily rooting for the Yankees and the Mets only so that I can watch Cleveland play them and beat them in the playoffs. So there is still, a thermalized disk in the inner regions that still acts like a gray body and emits in the UV, for example. If anything, I think it's a good thing that this disk is slightly cooler, because there's this problem that the peak of the UV for the traditional Shakura-Sunyaev model is too hot generically. So this is somewhat cooler. And in fact, actually, because of the lower optical depths of the disk, sort of Comptonization effects that you need for sort of the soft excess are more prominent, and they sort of fall out very naturally here. So you definitely get a Comptonized component as well into the EUV. I think, because this is just based on looking at things like opacities and some simple analytic calculations. We're trying to answer this with these more sophisticated radiative transfer calculations to say the real answer to your question. But I think this actually goes in the right way relative to that standard disk. This will shut down if you go to lower accretion rates. We had an analytic paper modeling these, extrapolating a lot. Much like the standard disk model, if you go to about 1% of Eddington, everything sort of falls apart in the central region, in the sense that the cooling becomes too long, it becomes too optically thin, and you predict something like a state change to more like an ADAF, again, like the standard lore. It's interesting. It was surprising to me that it happens right about the same accretion rate in Eddington units, actually. But yeah.
All right, maybe we have one more in the room, and then otherwise we'll head outside.
There seem to be some interesting implications for both LISA and PTA in terms of sort of the microelectricity.
Yes. Yes. So there's a couple of things that are tantalizing here. So one that I don't know if it may go in the wrong direction, but we mentioned earlier, but there's a student at Caltech working with Elias Most, Haiyang Wang, who's been starting some simulations of circumbinary disk simulations with these magnetized puffy disks, because we know that the ability of the circumbinary disk to harden the binary is very sensitive to things like the disk thickness and radial profile. So that should be different in these models. Another interesting thing that let me just pull up this plot. That we saw in these simulations I described by Yanlong. So when you have these star clusters bringing black holes into the center and assembling into this superstar cluster, they brought more than one in, and a few got kicked out, but you were left with if you actually look really close, you can see there's two stars here. It's two black holes, and they actually end up in his simulation at very equal masses and like within 3% or something of the same mass, which may be, people have talked about this for things like twin stars, that if you have a circumbinary disk, there's a mechanism by which the accretion disk sort of switches which one is accreting to keep them roughly equal mass. That may be happening in this simulation, which would be really cool for things like LISA. But and then there's a host of other, I mean, we were just talking about, implications potentially for MRIs and other things like that that we haven't begun to look at yet. Yeah.